Okay, can we start? Okay. One more, 1 hour more organic before the weekend starts. So let's get this over in that we are going to do this together and discuss a little bit on the two scenarios which we embarked on last hour. We talked about a reaction where we have a substitution of a leaving group with a nucleophile. And we put up two scenarios how this could work. We have two mechanistic proposals. And so let's see what we can do with this. And so the first mechanistic proposal out there, and of course you know all this, has been that the rate determining step is the dissociation of your starting compound forming a carbocation, and by a nucleophile, the nucleophile comes in the fast second step and giving you the product. And this would be consistent, and that is actually the experiment we would do here first. This proposal would be consistent with the first order kinetics, and that is that the reaction rate is only proportional to the concentration of our starting compound. And the other proposal would be that let me see that if I can do this from this way here, that we have a simultaneous approach of the nucleophile, and at the same time the leaving group goes away, and going through such a transition state, again this would lead to the product. And such a proposal would be consistent with the observation that the reaction rate should be dependent both on the nucleophile as well as on our substrate. So this would be simply the way we have done this here is we would have simply measured kinetics. So this would be second order kinetics. And then based on these based on these kinetics, we make a mechanistic proposal. And now we can ask ourselves, what would this mean? And then is this backed up by more mechanistic evidence? And so if we start here on the SN1 reaction, so here we would have reaction rate depends on the carbocation formation. This is the rate determining step. I could have drawn again the reaction diagram up here. So we would be in the situation that we would have the starting materials. We go through a intermediate. And this, of course, makes sense. A carbocation is a less stable intermediate, so it makes sense that this is energetically higher. And then in a second step, we would have the substitution reaction. So if and here we have SN2 reaction rate is dependent on both components. So let's start analyzing the substrate. If you know that the reaction should proceed especially well if a carbocation it has to go through the formation of the carbocation. What does this mean for the substrate? What kind of substrate should go especially well in this type of reactions? Yeah? Substrates with small ligands. Why should so the suggestion is that in the SN1 reaction, a substrate with small ligands, the reaction should go particularly well. Why is this? Can anyone support this argument? And what about the other argument? This reaction should go especially well if the groups are very big. What do you think? Yeah? Small ones, so again, steric and electronics, right? The magic sentence, and now the proposal would be here, if we look at our transition state, which we have drawn here, and we have to go in this more in detail, which of course you know already all the answers. But in the transition state, if I fill my R group here with life, simply based on the fact that we are having some kind of a carbon atom which in the transition state is surrounded by 5 groups, and before that it was surrounded by 4 groups, you would expect that this type of arrangement is sensitive to steric effects. Because in the transition state, there's crowding. You have to somehow accommodate an additional group, although there is, on the other hand, also a group already leaving. So if we go here on this side, again, we are talking about, in the moment, requirements of the substrate. Then we would think that high steric crowding around R should disfavor the SN2 pathway. Let's go back to the SN1 pathway. How is it here with high steric crowding? Think about, again, the rate determining step is the formation of the carbocation. Will this go easier if we have a lot of steric crowding in our starting material, or will it be more difficult? What do you think? Who thinks it's easier? Who thinks it's more difficult? Who's undecided? At least a number of hands went up for undecided. We have now a fourth category, don't care. Why are you undecided? There was one hand undecided here in the first row.
I didn't really understand the question because I was still writing.
So the question is, if you have a substrate where, let's fill this with any type of life. So we have our substrate here. And again, we have groups around. And the rate determining step is the formation of the carbocation, and purely based on steric arguments. We go to electronics in a moment, but just based on steric arguments. Will this type of reaction benefit from steric crowding, or will it be disfavored by steric crowding if I make these groups bigger? How is this? What's the angle in a tetrahedral on a tetrahedral carbon? How many degrees? Huh? In a tetrahedral carbon, it's 109. Exactly. And here? Here it is 120. So think about it. And SN reactions is very much like relationship between people. But think about this. You're not the whole person here. You're just part of this. Would you feel, if you are very big, which arrangement would you prefer? Would you prefer to be at this angle next to your neighbor? Let's pretend that these carbon substituent bonds will not really change. Or should this be the better arrangement?
Of course, the bigger angle.
Yeah.
If the other groups around the atom are bigger, it is harder for the leaving group to get back to the carbocation.
Well, careful here. It's a very good argument, what he said. He said, actually, this should go better, because obviously you have more room. Absolutely. I think there's no question about this. And you have, in the next problem set, there's one question where you are supposed to discuss hydrolysis rates of esters. And this is exactly a factor, because you will see that the rates dramatically change by the size of substituents. So I think we would argue this. And then he said, but now in the second step, which comes here, of course. Also, of course, the nucleophile for the nucleophile, it's much harder to now attack this. So, is this a relevant argument based on the assumptions we made here? That we say it's easier to form the carbocation, but it's also more difficult than to form the second step, the nucleophilic product.
What I meant is that the leaving group is more difficult for the leaving group to get back to the carbocation. Whereas assume that the nucleophile is smaller than the leaving group. So
yeah, that's an assumption we don't know. So the question is, and that's of course always the question, what we have assumed here is that the reaction goes in the direction that the nucleophile displaces the X group. You have always the big question here that of course also you have always the question that this might be reversible. And the same thing, of course, here, the whole thing might be reversible. If you choose your nucleophile in a way that your leaving group is actually the better nucleophile, the reaction will not work. So let's assume that the reaction works. But my question here is again, so we say that the steric crowding should help the formation of the carbocation. But then at the same time, it might be argued that the nucleophile now in the second step might have it more difficult to attack the carbocation simply because there's not enough room. Based on the assumptions we have made, is this a valid argument that you say, I cannot decide? Here I would say formation of carbocation, steric effects, the bigger, the easier it should be. And so the better the reaction should go. Now the counter argument is, but hey, the nucleophile, it's also harder for the nucleophile to attack. Is that a valid argument?
No, it's not.
Why not?
The formation of the carbon pattern is the rate determining step.
Exactly. So the rate determining step, that's of course only a proposal and an assumption. But if we assume that what we have written here is correct, then the rate determining step determines the reaction rate, somehow obvious the way I phrased it. And so only this then is decisive. And the hump on the next, if you look at the reaction diagram again, so this is a barrier to overcome to the carbocation. And then this here is much smaller. And so this is what is relevant. And maybe one can construct a scenario where indeed this is so crowded that the nucleophile cannot come back. But then you're changing the assumption that the rate determining step really is the carbocation formation. If you really would come into a scenario that the carbocation cannot be attacked any longer, obviously you would increase this barrier by a lot, and at some point the rate determining step might not be clearly any longer the carbocation formation, which, based on the fact that organic compounds try to be neutral, this is always the higher energy, the rate determining step, than the recombination of two charged species. So here we would say steric effects steric crowding should favor the carbocation formation. Okay, what about electronics? As you all know, steric arguments and electronic arguments are there for everything. How do you think the electronics will influence carbocation formation here. Yeah?
When they have a plus I effect, it's good for the stabilization of the carbocation. And if they have some minus I effect, it's bad.
Okay, so it's argued that he says already, he names a specific effect. He says if you have a plus inductive effect, it should stabilize it. If it's a minus inductive effect, it should destabilize it. I think in general what we can say is any type of electron donor, no matter if the donor comes by inductive or mesomeric effects, any type of electron donor should favor, again, the R plus formation, and therefore accelerate the reaction, right? Because keep in mind, anything which favors the carbocation formation, that's the rate determining step, will accelerate the reaction. How is it here? Donors, acceptors, or doesn't care? How is the situation in the SN2 reaction? Yeah?
It doesn't matter because it's one step, and the main part is about the steric effects.
Okay, now let's still focus on the electronics. So the proposal is here, it does not matter. And I guess the reason for this is that what you're saying is here, we do not really have a charge here building up. But think about such a transition state in the moment. The new bond is not really formed yet. On the other hand, there is bond dissipation already. And how is it, does anyone remember bond strengths, or did our physical colleagues teach this already, bond strengths with lengths, bond lengths, distance? That is something like r to the power of 6. So the moment you start elongating a bond, a distance between two atoms, you go over exponentially away from your bond strength is decreasing. And so what this means is that also here in the transition state, this carbon is really depleted by electrons. Not as dramatic as in the SN1 reaction. Here we have a free carbocation. But nevertheless, also in this transition state, what we typically have is we have positive charge building up. And then we have negative partial charges around here. And so with this realization, it's also true that anything which donates electrons onto that carbon will also favor an SN2 reaction. So that's from a simply electronic point. So donor substituents also, let me put it this way, stabilize the transition state in an SN2 reaction. What are typical donor substituents? How could we test this? What would we do now? We could do a reaction where we have as a one substrate, let's say methyl iodide, and this is being treated with hydroxide. Or let me even Okay, and then we could have, we could exchange this. So you could make a whole series of reactions. And so assuming we have conditions which will favor the SN2 pathway, and we have not talked about reaction conditions. In the moment, we are talking only about the substrate. But based on what we have discussed so far, what would be your expectation? Which of these three reactions should be the fastest one? So we have 1, 2, 3. Who wants reaction 1, 2, 3, undecided, don't care. So I think there were like 6 people for reaction 3, and probably the rest was new category, even couldn't care less, right? So guys, do a little bit with this. So I would also tend strongly to reaction 3, because in the transition state, this is a benzylic position again, right? And so even though, and the argument would be, even though you start from a steric point of view, the phenyl group is clearly bigger than the methyl group or even just a hydrogen. So from the steric point of view, you would argue that this is probably the sterically least favored. From an electronic point of view, in the transition state, with a positive charge developing on that carbon center, that should be greatly stabilized by the phenyl group. And indeed, that is what you observe. Substitution reactions on benzylic halides are very fast, no matter if they go by SN1 or to SN2 reaction. So now again, we have steric and electronic arguments. Here we said steric arguments disfavor the SN2 reaction. Electronic arguments, donors are favoring it. Here we have steric arguments might favor it, and electronic arguments might also favor it. And as the quintessence, and you know this, of course, I think, is then what type of substrates, if you look at the substitution degree, so if we have these 3 substrates, and we are wondering if this would go, if these reactions would undergo reactions by SN1 or SN2, based on what we discussed. And then now this is of course something based on which you then have to prove experimentally. But here, what do you think? The primary halides, is this okay for SN1? And the answer is no, it's not. Simply because the primary carbocation is so unstable that it would not form, the SN2 reaction is okay because there is not so much positive charge building up in the transition state. And on the other hand, it's not sterically very crowded. Tertiary, let's go here. Tertiary is okay for the SN1 based on the fact that you're forming a tertiary carbocation which benefits from inductive effects here. Sometimes even you have like phenyl groups or so, or allyl groups, vinyl groups, which you will have an additional benefit by mesomeric groups. And on the other hand, this type of reaction does not work with an SN2 reaction in an SN2 pathway simply because the substrate is too crowded to allow the nucleophile to approach. What about this? This is a situation with the secondary. It's like this class here. Maybe, maybe not, or don't care. So here, both is okay. So could work, or let me put it like this. It's okay, it can work, and it depends. Here it depends very strongly on the reaction conditions. Now, having said this, there are some interesting substrates you should be aware of, and one of them I would like to show you. What about this situation? What do you think, what type of substitution will be possible here? So you have, on what kind of carbon is our leaving group? This is a primary carbon. And here we have a tertiary substituent, but not directly on the reaction center, but one basically, or the tertiary group is a substituent on that center where you would like the nucleophile to approach. And the question is, will this work by SN1 or SN2? What do you think?
I think it's a special case because
Yeah.
you have SN2 here, and then you have a lateral shift.
You think already further. So the question, the answer was you might have SN2 and then something subsequently might rearrange. The point is these type of substrates do not react in either SN1 or SN2, because here you have created something very difficult. It cannot really do an SN1 reaction because it would form a primary carbocation. But it also cannot really do an SN2 reaction because if you build this, you will even see, if you make a model in the computer or just build it with a ball-stick model, you will see that this group shields this center actually even more than if it would be a tertiary center directly. So a type of attack here is impossible. And this makes these types of substrates really not accessible. And if you do a planning of a synthesis and you run into this situation, that is something you need to avoid because it does not work. This type of rearrangement, this position here is called has a special name. It's the neopentyl position. Simply the fact that you have the reaction center combined with the tertiary substituents. So neopentane has been, if you look at this here, you have 1, 2, 3, 4, 5 carbons. This was the trivial name for this alkane, was neopentane, and so the whole arrangement has a neopentane situation. And if you address the center, you would say you try to do a substitution in a neopentyl position, and that is simply not possible. Now, we argued that this is not possible based on the idea that in an SN2 reaction, the nucleophile is approaching from the backside. We have a backside attack, but keep in mind, this was a proposal. That is what we proposed. But on the other hand, why not this? Or any other angle? What would be your arguments? Without knowing anything, you would say there are steric and electronic reasons for everything, right? That's even without knowing the answer. Again, this would have been a good answer. Steric arguments, I think we can see very easily here, right? If the nucleophile comes from the backside, it will avoid clashing with the leaving group. And so that certainly from a steric point of view makes a lot of sense that to approach from here, that is the sterically least crowded trajectory. Is there also an electronic argument for the backside attack? So the approach backside avoids crowding with the leaving group. Is there an electronic argument for the backside attack? Yeah?
The leaving group is fully electronized. So the nucleophile was now negative.
Okay, so the question is that electronic or is that again steric? What you're saying is a good argument. You say the nucleophile is somehow negatively charged or has some free electron pair. I have always drawn the nucleophile here with a negative charge. There are also, of course, neutral nucleophiles, but nevertheless, at least they have to have a free electron pair. And then the leaving group is taking also the electrons with it, so it leaves also usually as an anionic species. Again, there are also neutral leaving groups if this was positive before. And so the argument is both of them somehow have high electron density, and there's of course repulsion, and they would like to avoid this. So although you argued on electronic density of these, I still would regard this as a steric effect, right? Because groups simply avoid each other. Steric crowding is always usually by avoiding electrons or negative charges and so on. Yeah. Which orbital is the nucleophile attacking in this type of scenario? What are we doing? We are loosening in the end, a carbon X bond. But again, we need some kind, if the nucleophile is approaching, it needs to interact with some kind of orbital of this compound. And which orbital is this? It somehow interacts with our bond here, right? So we have a sigma orbital. We have a sigma orbital here of our bond. Is the nucleophile interacting with the sigma orbital of this bond here? Probably not, yeah?
No, it's attacking the corresponding anti-bonding.
Exactly. It would not make any sense to interact with the bond here, because this is a filled orbital. Our nucleophile has somehow a free electron pair, and so it would not make any sense if a filled orbital would interact with the filled orbital. It should interact with the corresponding anti-binding orbital. And where is this anti-binding orbital located? Yeah? It's on the other side, exactly. So if we have the bond, so the way you construct the anti-bonding orbital is you look at the bond, and this comes, of course, if you think about how this comes from, then two of your sp orbitals, which are colored in this way, are overlapping with each other. And this is forming the sigma bond. So this is sigma Cx. And then the other kind of combination would be where you have the clashing. So basically this is the disfavored orientation. Which then leads, so if we have our nuclei here, leads basically to a situation like this. So in other words, if you construct the anti-binding orbital, you would expect that the lobes are exactly here. This would be the sigma star Cx orbital. And so this is oriented exactly away from the Cx bond. And now think about this. If the nucleophile starts interacting with the sigma star Cx bond. So we have the Cx bond, and the Cx bond is described by a filled sigma Cx and an empty sigma star Cx bond. If you start now putting electrons into the sigma star orbital, what does it mean for the Cx bond? Is this additional electrons making the bond stronger or weaker? Yeah? It's weaker. It's an anti-binding orbital, right? So it makes it weaker, and that is exactly, of course, what we see. We see the nucleophile is approaching, and by this approach of the nucleophile, the leaving group is leaving, because the bond becomes weaker. And so I think this is a very nice picture which exactly shows this. Okay, I will show you next lecture a very famous experiment which has actually proved this. Because think about this in the moment. All we do here, these are models. Nothing is proven. But once you have a model, you can construct experiments which can then support your theory or discard it, and so you have to look for a new theory. And I show you as the so-called Eschenmoser experiment, which exactly proved that this backside attack is absolutely necessary in an SN2 reaction. I wish you a wonderful weekend, and I see you on Wednesday.